Hi, my name is Alex Guardo, and I'm a biomedical engineering graduate student in Binghamton University's 4+1 program.
And I'm Ash Spina, a first-year biomedical engineering PhD student in the lab of Dr. Guy German.
And we are researching the mechanical properties of motorcycle helmets upon high-energy impact events to better understand the forces experienced by the rider during automotive incidents. Let's check it out!
Motorcycle helmets are the essential barrier between the rider's brain and the external environment, functioning as the protective shield from direct impact in case of a motor vehicle accident. For this reason, it is essential to pass safety standards outlined by the Department of Transportation, including penetration testing, as is being shown in this video. In order to pass DOT penetration standards, a penetration striker weighing about 6.5 pounds is dropped from a guided freefall rig from almost 11 feet.
The purpose of this experiment is to compare the mechanical properties of helmets composed of various materials. Dart height after impact will be measured to quantify the amount of energy transfer from the helmet back to the striker. This will provide insight regarding the amount of energy the helmet is absorbing or dissipating upon impact, as well as giving us an estimate of how much energy the rider's head would experience.
Following footage was shot with a regular iPhone in slow motion, which accounts for an imaging speed of about 120 frames per second. The dart in this take is traveling at about 7 meters per second and makes a significant impact on the helmet. We further slowed this footage to illustrate the dramatic loss of data when imaging an object moving at high speeds with limited frame rates. This is demonstrated by the choppy downward movement of the dart as the footage progresses.
In order to capture higher frame rates at full resolution, a lot of high-powered lights are needed. We are attempting to illuminate 3 focal points for data collection, including the site of impact on the helmet, the dart's descent, as well as the dart displacement from frame to frame using the ruler as a point of reference for velocity and energy calculations. Our setup includes 4 high-powered LED spotlights aimed directly at these significant areas.
These images now illustrate that even at 500 frames per second, the dart travels a significant distance, indicating the high velocity. Using a frame-by-frame analysis method, we can calculate both the estimated velocity during the dart's descent as well as the energy reflection utilizing the dart's recoil after impact.
Much of our work up until this point has been in standardizing our guided freefall penetration test setup for optimal imaging. We're enthusiastic about beginning data collection on our helmets under different environmental conditions and points of impact this semester.
It is our hope that our research produces quantitative data on the mechanical properties of various motorcycle helmets and provides valuable knowledge to motorcycle riders about head trauma safety. Thank you for listening.